learning forces. We're very excited, and today we're going to look at Newton's second law. Now, we've looked at first and third, and we've looked at friction. Basically, now we're going to start to look at what happens when our forces are unbalanced, when we have a net force. Newton's second law is incredibly important. Okay, it's one of those sections that you're going to get asked over and over and over and over again. It's very, 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 very important. Okay, so let's put it in context. We need to talk about why is it easier to throw a tennis ball than a bowling ball? Tennis balls are small, okay, they're light. Bowling balls are big and heavy. But why is it easier? And I know we're going, oh, because of the mass. But what about the mass? Okay. Next question. Why can a soccer ball be made to go faster by one player than by another player? When another player kicks it harder, why does it go faster? It's the same soccer ball, has the same mass, has the same shape. But why is it that if you kick it harder, it'll go faster? How does this all work? How does the mass of the object and the force we exert on the object affect the way the object moves? Those are important questions for us. So, we've looked at a whole bunch of stuff already. Properties, types, representation, components, frictions, force and motion last time. Now we're going to put Newton's second law. It's still about motion, but it's a very specific law that we're going to look at. So, what are our key words? Mass. Mass is very important. Mass is how much matter something's made up of. We use the word weight incorrectly every day because we'll say to somebody, what's your weight? And they'll go 20 kilograms. That's not what they've answered. They've answered what is their mass. So mass is measured in kilograms. Mass is very important. We're going to look at acceleration. Acceleration is the rate of change of velocity. How does the velocity change? Now remember, acceleration may be positive or it may be negative. It may increase, it may decrease. It all depends on the situation. We're going to look at net force. We've done net force over and over again. That's the resultant. When we add all the forces acting on the object together, how could we replace those by a single force? And then we're going to get to Newton's second law. So we're going to look at it in terms of an equation and a statement. Okay, and it's a long one. So let's look at Newton's second law, and we're going to break it down because we've spoken about mass and force, so let's break it down. The first part is what is the relationship between acceleration and net force? Now, acceleration is directly proportional to net force. What does that mean? That means that if I make the net force bigger, acceleration gets bigger. They go together, okay? Net force, remember, is when we add up all the forces acting on a body and we replace it with a single one. That's the one that changes the motion. Now, I'm not telling you that it means that acceleration is going to be a positive or a negative. It depends on the net force, okay? Directly proportional means that if I double the net force, I will double the acceleration, okay? Acceleration depends on the net force. So that's the first relationship we're going to look at. The second one is mass and acceleration. Now, acceleration is inversely proportional to mass. In other words, if the mass gets bigger, the acceleration gets smaller. And you will know this logically, you know this instinctively, that when an object is really big and heavy, it's difficult to move it. That's what we're talking about here. But inversely proportional means that if the mass doubles, the acceleration will become 2 times smaller, okay? Acceleration depends on mass, which is why we put it first in the equation, okay, and in the statement. So if we come back to our mind map with all our concepts, we've been looking at Newton's second law, all right? And what we've done now is we've done basic explanations of what how acceleration is related to force and how acceleration is related to mass. We're going to take a quick break, but when we come back, we're going to do a little bit of an experiment just to show you that I've been telling you the truth. Okay, so we're going to take a quick break, and I'll see you in a little while. Welcome back. Now we need to get into the nitty-gritty of Newton's second law because it's really important. Okay, so we're still looking at Newton's second law, and what we're going to do now is what happens when the force applied to an object changes, but its mass remains constant. We're going to look at a relationship. Now, what you have to remember here is that we can't change more than one thing at a time. So if I'm looking at acceleration and applied force, I've got to keep mass constant, otherwise it doesn't work. So we're going to do a quick simulation, okay? So what I've got here is this is my setup. Over here, this is a trolley. We will talk about in your questions, they'll say dynamics trolley. It's just, this one looks like it's made out of metal. It's usually a little wooden block with wheels that can roll along a table. It's connected via a string to a pulley system. And over there, we have a ticker timer. Now, all a ticker timer does is it makes dots on a piece of paper. As the paper runs through it, it makes dots. Those dots are made at a constant frequency. So it makes, say, 50 dots in 1 second. The paper changes how fast or how slow it goes through it. So the distance between the dots tells us whether the object was going really fast or really slow. The trolley has a set mass. I'm not going to change that. I'm going to keep that the same. I'm going to put an applied force. The applied force is this, which now hangs on my pulley. What I'm going to do is, if you look, the mass on the string over there, that's telling me what my applied force. I know it's in kilograms, but we would times by 9.8 to get the force. We're not going to worry too much about that, but the mass of the cart stays the same. I'm going to release it, so it's going to go quite quickly. There we go. We've made a ticker tape. I know you can't see it yet. Don't worry, because here it is. So there's my tape, okay? And if you look at the tape, you can see, because the cart's accelerated, that the dots get further and further and further apart. So that was with quite a small force acting on the cart. Let's go back. Now I'm going to make the force that I'm applying bigger. So I'm going to add, I'm going to add more forces. So now I've added an extra 100 grams. So it's bigger. I'm going to do the same thing. I'm going to release the cart. There we go. We've made the dot. Now when I look at it, can you see that we actually have bigger spaces? Okay. Let me just go back and let you see. So there's the 1.5. There's more dots on the same. Look at the length of tape. That's always going to be the same. There's more dots when we have the smaller force, okay? When we have the bigger force, there's fewer dots in the same space. That means the dots are further apart because my object was moving faster. And every space is bigger because the object is accelerating. Okay, let's do one more. So let's close that. Let's add some more. Oh, no, they're taking them off. I don't want to take them off. Let's put them on. So I'm going to make this significantly bigger. Okay, I'm going to release it. It goes even faster, and I'm sure you saw that. Let's get to the third one. Oh, come on. Oops. There we go. There's my third tape. No, that's my second tape. That's not what I wanted. There we go. Third tape, even fewer dots. Okay? You can see they get bigger much quicker. So what is that telling me? That as I increase the applied force, keeping the mass of the trolley the same, it accelerated at a bigger rate. The acceleration got bigger. Now, from the ticker tape, we can calculate that acceleration. We're not going to do that, okay? That's actually something you should hopefully do in a practical. But what I wanted you to see is by increasing the applied force, and we're making an assumption friction stayed constant, okay, the acceleration gets bigger. But how do we put this into a way that makes sense for us mathematically? So, we're going to look at what happens. Acceleration is directly proportional to the net force when mass remains constant. I have to have that little part on where mass remains constant. Mass is a variable. Mass affects acceleration, so I can't look at both at the same time. What does this directly proportional mean? It means this. If, oh, no, that's not what I wanted to do. There we go. If the net force increases by a factor, acceleration increases by the same factor. This means that if I double the net force, I double the acceleration, same factor. If I make the net force 4 times bigger, the acceleration will also be 4 times bigger. They change by the same factor, by the same multiple. But it does the other way around as well. If the net force decreases by a factor, then acceleration decreases by the same factor. So we spoke about increase, so what this means for us is if I make the force half, so I make it 2 times smaller, acceleration is also 2 times smaller. So they work together, they change by the same factor. We need to be careful when we describe this. Because it's directly proportional, we cannot describe it as simply being if net force increases, acceleration increases. Because that tells me that it can increase by, doesn't have to be the same, but it has to be the same factor, or decreases by the same factor. It's very important, okay? But we have to look at it in terms of a graph, okay? So when we look at this in terms of a graph, the graph will be a straight line. This is beyond important in terms of your understanding, guys, because when we look at these graphs, we get a nice straight line, okay? But the graph has to go through the origin, has to go through that 0 point, which makes sense, because if there's no net force on an object, it's not going to accelerate. We know this. So of course it can go through the origin, but it makes a nice straight line. When we do this in practice, often not all the points sit on the line, but we draw a line of best fit. Okay, so acceleration directly proportional to net force. Now hopefully you know the symbol. We have seen it before when we did friction. Remember that is the symbol for directly proportional, and acceleration comes first because acceleration is the dependent variable. We change the net force to change the acceleration, okay? Acceleration can't change the net force. It's dependent on the net force, okay? When we look at the graph, the gradient of the graph is the change in A over the change in F net. If we look at this in terms of maths, you've done graphing, okay? Remember in maths, we would probably write this as, I was about to write an X, but it's not, it's a Y. Okay, so this would be Y2 minus Y1 over X2 minus X1. Acceleration is on the y-axis, F net is on the x-axis, okay? So we don't use the y2 minus y1 and x2 minus x1 because we they're not labeled as y and x. We use them as we've labeled them a over f net, okay? And it's changing. Please don't forget the delta sign. Don't forget the triangle, because there's a change. You can't use a point, you've got to use 2 points to calculate the gradient. What's important is because it's a straight line, the gradient is a constant. That constant has meaning. We'll look at that a little bit later. It's just a constant, okay? It's a straight line. We all good? All right. So, what happens when we keep the mass constant? No, when we keep the force constant. We've done mass constant. So what happens when we change the mass, but we keep the applied force constant? Okay, so that's where we're going to now. All right, so let's go back to our app. Okay, let's just actually get rid of the ones we had. What we're going to do now is I'm going to keep the mass on the string the same. So I'm going to take those away. Let's keep it at 1. This time, I'm going to change the mass on my cart, okay? We're making a very important assumption here, that with that applied force being constant, then I'm actually keeping friction constant as well. This is a simulation, so we can assume it, because in a simulation, we can make it in an ideal situation. That, of course, is more difficult in reality, because as I add more mass to the trolley, it's going to experience more kinetic friction because the normal force increases. We're not going to stress about this now. We've got an ideal situation. So I'm now going to add mass pieces to the trolley. We're going to release the cart. Okay, there we go. Okay, so we have our fourth tape. Okay, and remember, just like before, we're looking at the distance between the dots, okay? So we've got this one. It was quite heavy, so we're going to look at how many dots we have in the space. Now I'm going to increase the mass, so we're going to do another one. So there we go. Let's make the mass on the trolley bigger. I'm going to add more. Oh, no, add. There we go. So now I've made the mass bigger. It's heavier. The net force, the applied force is constant. Let's release it. So there we go. Hopefully, and I know it's hard to see, you can see it's actually going a little bit slower. So let's look at the tape. Let's find it. There's my fifth tape. Let's put it up. We actually have more dots now, because it's going slower. So just quickly, let's look at tape 4 again. We can count them, 2, 4, 6, 8, 10, there's 12 dots, okay? Tape 5, we've got 2, 4, 6, 8, 10, 12, and a little bit extra. So there's more space. Let's make it even heavier. So now I'm gonna add more. Let's make it significant, okay? So I'm going to add all the mass pieces. Now let's release it. You can definitely see it go slower, okay? Let's get the string. 2, 4, 6, 8, 10, 12, 14 dots this time. So it's going slower. As I increase the mass of the object, the acceleration got smaller. So now we know there's an inverse relationship. I'm not using the word proportionality yet, but there's an inverse relationship between them, okay? Mass got bigger, acceleration got smaller, got slower. So what I can say is that they are inversely proportional. We are going to prove it. Okay, inversely proportional. As soon as I use the word proportional, the factor that it changes by becomes important. Very important. So, inversely proportional means that if mass increases by a factor, acceleration decreases by the same factor. This tells me that if I double the mass, so I make it 2 times bigger, the acceleration will become 2 times smaller. If I make the mass 3 times bigger, the acceleration will be 3 times smaller. The opposite also works. If mass decreases by a factor, acceleration increases by the same factor. So if I make the mass 2 times smaller, the acceleration will be 2 times bigger. If I make the mass 10 times smaller, the acceleration will be 10 times bigger. Okay, it works in the opposite. We have to look at the graph. So, those are the graphs we're going to get, and I'll talk about those in a second. Acceleration inversely proportional to mass. We get a curve. Here I need you to listen very carefully to me. When we talk about this, often you'll tell me as soon as I get this nice curve, that it means they're inversely proportional. No, it doesn't. It means that there's an inverse relationship, that as mass gets bigger, acceleration gets smaller. We have to prove they're inversely proportional, which is the second graph, okay? So we have to get this graph. We have to draw a graph with 1 over m because of this relationship, that they're inversely proportional. This graph has to go through the origin. It must, it must, it must. So you've got to draw the second graph where you invert your independent variable, m, what's on x, okay? And it must go through the origin. This feels weird that it goes through the origin because you've got a 0 for a mass. Don't worry about that. The straight line graph is a proof. It proves to me that they are inversely proportional. That's really important. This curve simply says to me that there's an inverse relationship. The second curve with the straight line proves that they are inversely proportional, but only if it goes through the origin. That's very important. It's the second part there, okay? So, we're going to take a short break. When we get back, we're going to put these two relationships together to give us a mathematical equation, okay? So, we're going to take a short break, and I'll see you in a little bit. Welcome back. Now, let's put everything together that we've been looking at, okay? So, before the break, we looked at the relationship between mass and acceleration and force and acceleration, but we need to put them together. So, here we go. That's what we're busy with. We need a mathematical expression. We know, we did this before the break, that acceleration is directly proportional to F net, and we know that acceleration is inversely proportional to mass, which is why we put 1 over m here. This isn't that helpful for us, but we can combine these. Why? Because both of them have acceleration in them. So if I put them together, I can state that acceleration is directly proportional to F net, because it's at the top, inversely proportional to m. This is nice. It's a mathematical expression, but it's not useful for calculations because of the proportionality sign. We have to get rid of that. The way we get rid of that sign is by getting a constant. The constant is 1, okay? And that's been found from calculations, so you don't need to worry too much about it. But what it means for us is I can take that proportionality, get rid of it, put an equal sign in, I put in my constant, and I have F net over m. When you look at that, you go, hang on, wait, that looks like something I've seen. It's an equation. Do we write ones with multiplication? No, we don't need it. So you probably would have seen it like this. Now it's definitely looking like something you know. But we don't often use it in this context. We manipulate it so F net is at the front. That gives us the equation where F net equals MA. You have absolutely seen that, okay? The nice thing about this equation is it's given to you on your information sheet. But there's a big NB here, big important thing. This must be there. You have to put the subscript. You have to put net. It is a very, very specific force, okay? So if you write F equals MA without the net, you get naught. That equation doesn't exist. So F net is the net force measured in newtons. M is the mass measured in kilograms. And A is the acceleration in meters per second squared. What's nice about this equation? Mass is a scalar, so we don't worry about direction. F net and acceleration are both vectors. They have direction. Their directions are the same. So if F net, your net force, is to the right, acceleration is to the right. It's not about the applied force. It's about the net force. So we're going to have to work that out as we go along, okay? Let's do some calculations. Well, before we get to the calculations, let's get to the statement. So, Newton's second law statement. We like asking this one. Very important. When a resultant or net force, you don't have to put both words, you can use either, acts on an object, the object will accelerate in the direction of the force. Direction of the net force, direction of acceleration, the same. Now be careful with the language. At an acceleration directly proportional to the force, inversely proportional to the mass. It's a long statement for Newton's second law, but we're looking for a lot of things. We're looking at, for number one, direction of the acceleration is the same as the net force. Number two, acceleration is directly proportional to the net force. And number three, acceleration is inversely proportional to the mass. So you've got to have all three of those things in to make this a complete definition. Okay, it's a very, very, very important one. Now we can do some questions. So here we go. We've done all of this. Basically, we're starting to bring all of this together, which is great. Here we go. An object with a mass of 100 kilograms accelerates at 12 meters per second squared to the right. I'm giving you a direction. You can't change that to east or north or south or west. You keep it to the right. They want the net force. They haven't given me anything about friction or the normal force or any of those because it's not important. They just want the net force. Okay, so we got the question again. My best tip for you is to write down what you know, because sometimes the problem isn't that you don't understand the work. The problem is you don't know which equation to use because there's lots of stuff going on in the question. So we write down what we know. I know the mass is 100 kilograms. I know the acceleration is 12. And they want F net. Well, I can see from that exactly which equation I need to use. F net equals MA. So it's going to be 100 times 12. Now I know some of you can absolutely do this in your head. But remember, when you get into an exam, you get a little stressed. So we're going to use the calculator to be on the safe side. Okay? So we're going to go 100 times 12, which gives me 1,200. Okay? newtons. Force is a vector. A vector means I need direction. It was going to the right, so this is also to the right. Really not so bad. All right, it's gone over there. There we go. Let's do another one. Okay. An object with a mass of 100 kilograms, same thing, accelerates at 12 meters per second. Now it says if the mass of the object doubles, what must be the magnitude of the force to cause the same acceleration? So what have we done here? We've changed the mass, but we want the same acceleration. A little different to what we've been doing up till now, because we've always let the acceleration change. So in order to have the same acceleration, something needs to happen with the force, okay? So the mass doubled. Well, if the mass doubled, it was originally 100, so now it's going to be 200. The acceleration is still 12. We want F net. Really wasn't that bad. Same equation. So we want F net. We know this is 200 times 12. Again, let's do it on the calculator just to be sure. We get 2,400, okay? And again, it's still going to the right, so we're going to say it goes to the right. Don't worry about when they say things double and stuff. You can change your values to match them. Do the calculation again, okay? Now we get to the fun ones. This time I don't give you net force. Now we've got two forces acting on a 13 kilogram box. Mass, very important. I want the acceleration. I've got two forces. I need to find net force. So we know mass, which is 13. I want the acceleration. I need the net force. What that means for us is we've got to choose a direction as positive. This is your choice. Try and be a little logical about it. So if we look at our diagram, the 60 newtons to the right is the big one. It makes sense to make that the positive direction. So I'm going to make to the right positive. So the first thing I need to calculate is F net, which means it's going to be the 60 Newton force minus the 20 Newton, because the 20 Newton is going to the left, so it's a negative value. That tells me that my net force is 40 Newtons to the right. I now have all the information I need. I've got F net, I've got M, I want A. So F net equals MA. F net is 40, M is 13. Now I want A. At this point, if you can solve for A directly on your calculators, you're welcome to do that. If you need to do all the maths, do all the maths, okay? So in other words, to get A on its own, I need to divide both sides by A. So I'm going to have 40 divided by 13. I definitely can't do this in my head. So let's just do it over here. 40 divided by 13. I get a fraction. We never leave as fractions. It's 3,08. Round off to 2 decimal places. 3,08 meters per second squared. But remember, it's a vector. I need direction. My net force was to the right. So that's to the right as well. Please, the fraction thing is very important. They don't accept your final answer as a fraction. It must be as a decimal. Okay? So, what have we learnt today? And this is very important. Acceleration, directly proportional to net force. That means we need to know the net force, so sometimes we're going to have to calculate it like we did in the last example. Directly proportional means that if we double force, we'll double acceleration. They'll increase and decrease by the same factor. Acceleration is inversely proportional to mass. They do the opposite. So if mass increases by a factor of 2, acceleration decreases by a factor of 2. So the one goes up, the other goes down, okay? But what we have to remember about both of these, acceleration depends on force. Acceleration depends on mass. Force and mass don't depend on acceleration. They determine the amount of acceleration. And then, of course, we've got the equation where F net equals ma. And will be given to you. Yay, we're happy. Net must be there. And, of course, with this equation, we know that the net force is in the same direction, well, the acceleration is in the same direction as the net force. Okay, very, very important. In the next lesson, we're going to bring all of this together. So we're going to take everything we've learned and we're going to put it together in one, okay, which is why there's no new concepts on the mind map. We've done all of this, okay, and it's very exciting. We're finally going to get to putting it in one section rather than the bits and pieces, okay? So I'm going to say goodbye for now, and I'll see you next time.